Swayam Prabha. Digital India. Educated India.
Welcome to week 2, lecture 10. So, this is the last lecture of second week and also the last lecture of performance characteristics of instruments and data analysis part 1. So, today we will talk about analysis of second order instruments. We have talked about analysis of first order instruments in the previous class. So, in this class we will talk about analysis of second order instruments. We will take an example of second order instrument and analyze the instrument, write down the modeling equations and show that the instrument is second order in nature. We will also briefly talk about step response of second order instruments. As we have seen, the first order systems are characterized by capacitance and resistance. Similarly, second order instruments are characterized by oscillations about its position of equilibrium and a damping that oppose these oscillations. So, in all second order systems, there will be an oscillations about its position of equilibrium and there will be a damping that oppose this oscillation. So, depending on the damping factor, the amount of oscillations will vary in second order systems. We will talk about more later in this class. The natural frequency of the instrument is the frequency of these oscillations. Friction in the instrument opposes these oscillations with a strength proportional to the rate of change of the output. The damping factor is a measure of this opposition to the oscillations. Some examples of second order instruments are U-tube manometer, pressure gauge, galvanometer, etc. So, this is an example of or schematic of U-tube manometer. So, this is a U-tube manometer. Commonly, it is made of glass tubes and bent in the form of U. These are the two limbs of the U-tube manometer. These two limbs are connected to different pressure sources. If the limbs are connected to two different pressure sources, the level of mercury in both the limbs will be different. If both the limbs are connected to the same pressure source, let us say both the limbs are open to atmosphere, that means same pressure is being applied on both the limbs, then there will not be any level difference in the U-tube manometer. So, the difference of level of mercury or manometer fluid within the manometer is a measure of difference in pressure in these two limbs. So, when the two limbs of a manometer are connected to two different pressure sources, the liquid in the U-tube oscillates with a frequency determined by mass of the liquid. The damping factor is determined by viscosity of the liquid and friction between the liquid and the tube surface. So, when both the limbs initially imagine that both the limbs were open to atmosphere, so they are connected to the same pressure source. Now, I connect this to a pressure source P1 and this is another pressure source P2, P1 and P2 are different. As the figure shows, P2 is greater than P1. So, that is why this is pushed more. So, when you do this, there will be oscillations of this manometer liquid and these oscillations will be with a frequency that is determined by mass of the manometer liquid that is present within the U-tube manometer. These oscillations will be opposed by the viscosity of the liquid and also the friction of the liquid with the surface of the U tube. So, the damping factor is determined by viscosity of the liquid and the friction between the liquid and the U tube surface. Force measuring spring scale is another example of second order instrument. If I put a force here or if I put some weight here, this will oscillate. It is an example of second order instrument. Galvanometer is another example of second order instrument. Galvanometer measures current. So, the current to be measured flows through a coil. This is the coil that is suspended in a magnetic field. Rotation of the coil is induced by magnetic forces exerting a torque on the coil proportional to the current flowing through it. The property of the restoring spring and the moment of inertia of the coil decide the frequency of such oscillation. The damping of the oscillations is caused by mechanical friction. So, now we have seen few examples of second order instruments. Let us now talk about mathematical model of a second order system or second order instrument. So, we will start with the generalized mathematical expression for an nth order instrument and we will retain terms up to second order, so that the second order differential equation that we will get will represent a second order instrument. So, let us look at the nth order ordinary differential equation that we have talked about previously, that represents a nth order instrument. So, recall this instrument, an nth order ordinary differential equation with constant coefficients represents the variation of output with respect to time, and on the right hand side I have the input function. A second order instrument has an output which can be represented by a second order linear ordinary differential equation. So, if I retain up to second order terms, I get this ordinary differential equation from this general nth order ordinary differential equation. So, this represents a general mathematical model for a second order instrument. As we have done previously, let us divide this equation throughout by the coefficient of the zeroth order term. So, I get A2 by A0, A1 by A0, A0 by A0 and B0 by A0. I call this A2 by A0 as tau square, A1 by A0 as 2 zeta tau and B0 by A0 is k, the static sensitivity. So, there are three parameters in this second order instrument, tau, zeta and k. So, the equation can now be written as tau square d square y dt square plus 2 zeta tau dy dt plus y equal to k into x t, where x t represents input function such as step input, ramp input, sinusoidal input, so on and so forth. So, to get transfer function of the second order instrument, what I have to do is I have to take Laplace transformation of this equation and then take the ratio of Laplace transformed output by Laplace transformed input. So, if I do this, I will get this expression. So, the transfer function for second order instrument, which is y s by x s, will be k by tau square square plus 2 zeta tau s plus 1. For a first order system, we have seen the transfer function for a first order system. Let us say transfer function for first order systems was k by tau s plus 1. So, there are two terms involved, k and tau. In case of second order instrument, the transfer function for a second order instrument can be written as k by tau square s square plus 2 zeta tau s plus 1. We would like to make a point here that sometimes you will see the transfer function for first order system is written as 1 by tau s plus 1, and also for second order system it is written as 1 by tau square s square plus 2 zeta tau s plus 1. In other words, these two expressions I mentioned, the value of k is equal to 1. Say for a mercury in glass thermometer, we have seen the first order equation that represents a mercury in glass thermometer, we have written in two different forms. In one form, output was taken as x 0, x, you remember, that is the level of the mercury in the capillary. So, that is distance, a measure of distance. So, the relationship was there with input temperature and the distance which was taken as output from the thermometer. We also wrote another equation which are related, of course, where the input was the temperature and the output of the thermometer was again also taken as temperature. When the input was temperature, output was also temperature, the transfer function will be written as, for the first order system, 1 by tau s plus 1. So, in other words, when you have inputs and outputs are physically same quantity, the nature of the signal is same, the value of k will be equal to 1. So, the transfer function for first order system can be k by tau s plus 1 in general, but k will be equal to 1 in certain occasions, and this happens when the input and output are of same type of signals. For mercury in glass thermometer, input is temperature, output was also temperature. So, the value of k there will be equal to 1. You can verify it from the equation that you have derived. The same logic applies to second order systems transfer function as well. Now, let us quickly take a look at step response of a second order instrument. Specifically, we will give unit step input to a second order system and we will see the response when a such unit step input is given to second order instrument. So, unit step input is represented by this x t equal to 1 for all time t greater than 0. So, at t equal to 0, the input value is taken to magnitude 1 and maintained there for all time to come. We have seen previously that the Laplace transformation of x t equal to 1 is 1 by s. So, let us make now use of the transfer function equation, which is this. So, I have to put x s equal to 1 by s, I have done it here, and then I can rearrange to write this as this. I rearrange it so that it becomes easy for me to take inverse Laplace transformation, because if I now take inverse Laplace transformation, I will get y t. That means, how output y changes with respect to time. So, output as a function of time will be obtained when I take inverse Laplace transformation of this. If you do that, you will get different types of response depending on the value of zeta. So, this is what we obtain from the transfer function of second order instrument after putting x s equal to 1 by s, and then we rearranged and we wrote in this form. Now, you take inverse of this. Now, when you take inverse of this, depending on the value of zeta, we can have 3 different types of responses, or the y t, we will have 3 different types of expressions depending on value of zeta. Zeta can be greater than 1, zeta can be equal to 1, and zeta can be less than 1. So, depending on 3 such values, we can have 3 different types of expressions for y t. Now, when zeta is greater than 1, we get this expression, and this is known as overdamped response. Zeta is damping factor. So, when the value of this damping factor is greater than 1, the response I get is known as overdamped response, and this is given by this expression. When zeta value is exactly equal to 1, it is known as critically damped response, and we get this expression. When zeta is less than 1, what we get is known as underdamped response, which is represented by this equation. Look at here, this is a sine function. So, there will be oscillations. So, this is the radian frequency of this oscillation, and this is the phi value. So, depending on the value of zeta, we have 3 different types of responses. Accordingly, we call overdamped instruments, underdamped instruments, and critically damped instruments. So, for a critically damped second order instrument, you know the damping factor is equal to 1. For underdamped instruments, the damping factor zeta is less than 1, and for overdamped instruments, the damping factor zeta is greater than 1. So, they show responses which are known as overdamped response, zeta greater than 1, critically damped response, zeta equal to 1, and underdamped response, zeta less than 1. So, pictorially they look as follows. Please look at here. This is underdamped response. See, there is sustained oscillations because you have the sine function there. So, here zeta value is less than 1. So, you will have oscillations, the response will oscillate. For overdamped, you will get this response, and for critically damped, you will get this. So, oscillations will be reduced using the increasing the value of zeta. So, this once again shows the effect of this damping factor or damping ratio zeta on the step response for a second order instrument. If there is no damping, so zeta equal to 0, you will have sustained oscillations like sine wave. When you have some non-zero positive damping ratios, you will have oscillations, but of course reduced. C, you have 0.707, you see the oscillations has reduced now to a great extent. This is critically damped. So, this is the response and this is over damped. So, this even runs below the critically damped curve. So, these three are under damped response, critically damped response, over damped response. Please note one thing, that for under damped instruments there is oscillations, but it reaches the final value much more quickly than a critically damped or over damped instrument will do. So, second order instruments such as pressure gauge is generally designed as an under damped instrument with zeta value maybe around say 0.7 or so. So, then what will happen is the speed of response will be reasonably good and there will be oscillations, but there will be not much oscillations. You can look at this figure. So, this one represents zeta equal to 0.7. See, this is the time by which it attains the final response. So, this was the step input given at this time and this. So, my instrument should show this response finally with zeta equal to 0.2, it takes very long time. Zeta equal to 0.7, it takes somewhere here. Zeta equal to 1, it takes somewhere here. Zeta less than 1 takes even longer time. So, the pressure gauge, which is a second order instrument, is typically designed as an under damped systems with zeta value around 0.7 or so. Now, let us quickly take an example of U-tube manometer, and I would like to develop the mathematical model that describes the behavior or the dynamics of this manometer. So, basically we will try to develop an ordinary differential equation that relates input to the manometer and output from the manometer. So, let us consider a simple U-tube manometer. Let initially the pressure at both the legs are equal. So, initially you will have this as plane of initial rest. Suddenly a pressure difference delta P is imposed on the two legs of the manometer. So, now there will be differences of manometer liquid level, that is output of the manometer, and that is this 2 H or H around the plane of initial rest. Let us introduce these terminologies. A equal to cross sectional area of the tube rho is density of liquid in manometer, g acceleration due to gravity, m equal to mass of liquid in the manometer, which can be taken as rho A L, because rho times A is the volume, sorry, A times L is the volume and rho times A L is the mass of the mercury. A times L is volume, so you multiply volume with density, so you get mass of liquid in the manometer. V is velocity of the liquid in the tube, h is deviation of the liquid level from the initial plane of rest, L is length of the pipe, R is radius of the pipe or the U tube, and mu is viscosity of the manometer liquid. So, now let us apply Newton's law on the plane C. So, we can write the force balance equation as force due to pressure P 1 minus force due to pressure P 2 minus force due to liquid level difference in the two legs minus force due to fluid friction equal to mass of liquid in the tube into acceleration. So, sum of all these forces equal to m into F. So, force due to pressure P 1 is P 1 times cross sectional area of the tube. So, P 1 into A. Similarly, force due to pressure P 2 is P 2 times cross sectional area P 2 A. Force due to liquid level difference in the two legs is rho g A into 2 H A into 2 H times density, volume times density times acceleration due to gravity, and this is force due to fluid friction is mass into acceleration, which is rate of change of velocity. So, force due to fluid friction can be written as this from fluid mechanics, where small f is the fanning friction factor, and if you assume laminar flow, the fanning friction factor can be written as 16 divided by Reynolds number. So, if I put the expression for the Reynolds number, I will get this, and this finally will appear as this. Now, V, which is the velocity of the manometer liquid, can be taken as rate of change of h with respect to time. So, V equal to d h dt. So, finally, the force due to liquid level force due to fluid friction can be written as this. So, this is the equation we obtained in the previous slide. Now, V is dH dt. So, dV dt can be written as d2h dt square, and if we rearrange this equation, how do we rearrange? We divide this equation throughout by this coefficient, which is coefficient of 0th order. So, if we do that, I will get this equation. Look at this equation. This equation is a second order ordinary differential equation. So, if I call this tau square, this is tau square d square h dt square. If I call this 2 zeta tau dh dt plus h, and if I call 1 by 2 rho g as k, this is k into rho p. So, this is the equation we finally get. So, this parameter zeta, tau, zeta and k are obtained from this and this. So, this becomes very useful for designing a manometer. So, you know, if you want to make zeta less than 1, what sort of parameter values you should have. The transfer function can be written by taking Laplace transformation of this. Again this is output by input is equal to k by tau square s square plus 2 0 tau s plus 1. Note here, k is not 1 because your output is measure of length, but input is pressure difference. So, they are different signals. So, k cannot be 1. So, this is the end of week 2 and lecture 6 to 10. So, the major topics we covered are performance characteristics of instruments and data analysis part 1. Under this, we have talked about static characteristics and dynamic characteristics. We have also talked about general mathematical models of instruments. We have talked about first order instruments. We have taken examples and analyzed it, talked about step responses. We have also talked about second order instruments. We have taken examples, developed the mathematical expressions representing a second order instrument, analyzed it, also analyzed second order response. So, this ends lecture 10 or the last lecture of week 2. In the next lecture, we will talk about performance characteristics of instruments and data analysis part 2.